Okay, so in this video, we're going to talk about quantities and covariation. So we are in chapter 4. So children have a great deal of experience and knowledge about the world around them, but they generally do not have a lot of experience talking about quantities and change. And many of the powerful ways of thinking about quantity and change have roots in just simple visual and verbal activities. So these are very important. Okay, quantities unquantified. A quantity is a measurable quality of an object, whether that quality is actually quantified or not. When trying to quantify, reasoning about, and this is key, you want to reason about what changed and what did not change. That's very important. It's very important from an observational point of view. It's very important from a critical thinking point of view. The table below was used in a discussion about cookies and children. And this is a good example of visualization that will help clarify topics like this. So this is how the table works. The table overall is assessing a change in the quantity of cookies per person. So keeping with the theme of what changed and what did not change, if you increase the number of cookies, so I'm over here. So increasing the number of cookies is going to have an impact on how many cookies I get. So if you increase the number of cookies and also increase the number of people that are getting these cookies, I can't make a determination about how that's going to impact how many cookies I get. Okay? So there are two changes happening, and I can't figure out which change has more impact. However, if I increase the number of cookies and I decrease the number of people getting cookies, I am definitely going to get more cookies. That's going to be a positive change in the quantity of the cookies per person. If I increase the number of cookies and I don't change the number of people, I can also say that's going to be a positive change. I don't know how much of a change, but I can definitely say it's going to be a positive change. So let's go through the decrease. What if I decrease the number of cookies? If I decrease the number of cookies and I increase the number of people, I am definitely going to have fewer cookies per person. If I decrease the number of cookies and I decrease the number of people, that's indeterminate. I can't tell what the impact's going to have. If I decrease the number of cookies and I don't change the number of people, then I'm definitely going to have fewer cookies per person. Okay, let's go down to the last row. What if there is no change in the number of cookies? If there's no change in the number of cookies, but there's an increase in the number of people, that's going to be a decrease in how many cookies each person gets. No change in cookies and a decrease in people, that's a positive change in the amount of cookies per person. And if neither thing changes, so the change in cookies doesn't change and the change in people doesn't happen, then there's no change. So this table is a great way to quantify. It's also a jumping off point, as we can see on the next page of the video. If you take the discussion about cookies and people to a situation where you're going to try to compare fractions, it kind of makes that leap a very good one. So think about cookies and people when asking whether 3/4 or 2/7 is greater. So tell a little story with it. How about if we have the cookies be on top? So we'll have cookies in the numerator, and we'll have people in the denominator. Okay, so we can say yesterday we had 3 cookies for 4 people. Today we have 2 cookies for 7 people. Which fraction is bigger? Well, the 3/4 is going to be bigger with that reasoning. And so we can say that 2/7 is less than 3/4 using our cookie reasoning. So we haven't even gotten into fractions, and here we have a way to assess whether fractions are smaller or greater than one another. So we use the what changed and what did not change to analyze that problem. So let's continue that down below. Now here we have a very nice system of equations. So if I was teaching an algebra class, I would give everything variables, and I would set it up like this, and I'd be able to solve. So my M is my milk, the C is the soup, and the B is the bread. Okay, so I can get all my nice algebra answers. But we're not in algebra class right now. We're in a fractions class, and we're in a reasoning sections of the fraction class. So we're going to be looking at this situation, not algebraically, but just logically. And we're going to be trying to figure out what changed and what did not change, and see if we can get an edge on problem solving, because using critical observations is going to be key. So let's do that on the next page. Okay, so I gave us some space here to work on this. So I started out just looking at the first two purchasers. So A is buying and B is buying. So let's just compare A and B. Okay, so A buys 2 soups, 1 loaf of bread, and 2 milk. B buys 2 soups, that's the same, hasn't changed. 1 loaf of bread, hasn't changed. Oh, but only 1 milk. So don't I know by just looking at A and B that milk must be $1.50, because that's the difference between the two prices they're paying. And that is consistent with what I found when I did it algebraically. Okay, so that's one done just by comparing A and B and see what changed and what didn't change. So then what I did next was I looked at B and C. So looking at B and C, let's do a couple of things. I see that both B and C have purchased milk. I already know the price of milk. So can't I subtract $1.50 away from each of their purchase price and be focusing on only soup and bread? So let's do that. So B is going to have 2 soups and 1 bread. That's going to equal $1.50 less than $6.50, so that's going to equal $5. Okay, so then looking at the next one. Okay, so C is going to have 3 soups plus 2 breads, and that's going to be $1.50 less than what he paid, so that's going to be $8. All right, so let's see what's different between these two. So it looks like I could subtract away 1 bread and 2 soups from C's order. When I did that, I was left with, so let's see, I'm going to have 1 soup plus 1 bread, and that's going to equal $3. The textbook also explains this, but hopefully this is helping. Okay, so now that doesn't give me an answer yet, but it certainly does give me someplace else to go. So now with that information, I'm going to go back up to A. So I'm going to change again. And I'm going to say, what is A buying? Well, A is buying, so I'm going to look at A. A is buying 2 soups, 1 loaf of bread, and 2 milks. Okay, so I know some prices here. So don't I know that 1 soup plus 1 bread is going to be $3. Then A has another soup, and he has 2 milk, but the 2 milk are also $3, and he's paying $8. So far I've taken account of 6 of his $8. So doesn't that make sense that that 1 soup must be $2? And this is my soup right here. So yep, that's $2. Okay, so now we're ready to go and see if I can figure out the last piece, the bread. What does the bread cost by itself? So we can go back up to A one more time. So we're going to revisit A. I'll change my color again. And we're going to say, okay, so A is buying 2 soup. Do I know what the soup costs? Yes, soup is $4 because each can is $2. Plus a loaf of bread. Do I know the bread yet? No. So plus bread plus 2 milk. Do I know the milk? Yep, the milk is each $1.50. So that's $3, and he paid $8. So I'm taking care of 7 of the $8, so that must mean that the bread is going to be $1. And we have reasoned this out without using calculus, clearly, but without using any algebra. We have thought this through, focusing on what changed between the three individuals' purchases. So I think this was a really good lesson in how to work this through. So let's go on to the next page. So I want to talk another minute about quantifiable characteristics. So a good example is this water running in the bathtub. Because if you ask what's changing, is the water physically changing? No. Is the bathtub physically changing? No. Can I see a quantifiable change with either of their characteristics? And you would say no. So the physical description of the situation is that the bathtub is being filled with water. But the quantifiable or measurable characteristic is that the volume of water is changing. That is what can be measured. And that's where our focus would be. Another big thing at this point is to be able to discuss proportional relationships, and pictures are a great way to do that. So there's a couple of ways to talk about proportion. You can talk about proportion between objects. So this would be between objects. Okay? And I would say that our goal is going to be to talk about a scale factor. How are these related? Are they similar? Are they built in proportion? And they are. If we were to measure them, we would see that they are being changed proportionally. As opposed to, we can talk about proportions within an object. And within, you're looking for You're looking for an aspect ratio. So it's another way to measure proportion. This is within an object. These are rectangles, and I'm showing you the proportion of the length to the width. Okay, and there's a relationship there. Okay, so visualizing, verbalizing, and symbolizing changing relationships. When having children discuss proportion, it's useful to have children make verbal statements about changing relationships and to use arrows to note the direction of the change of each quantity. So with your little coffee cups, you can see that had gone up, that increased. Okay, so that was the scale factor. It's between two objects. Okay, let's go on. Our textbook provides us with two examples of these increasing and decreasing arrows that we can be using. One was with a balloon rising in the air, and the second was candy and sharing. So this brought up the idea of covariation, which is linked quantities are changing together. All right, so covariation and invariance. Covariance is when two things change together. Invariance is when the whole remains and maybe you rearrange the parts differently, but the whole remains unchanged. And the example they give us in the textbook is those little playing chips. And then another good word is analogies. So dog is to fur like bird is to feather. And these analogies help children understand proportional reasoning as well. Okay, so you're introducing this idea of proportional reasoning on many, many fronts. Okay, Quasar strips are huge. They are a great way to visualize different holes to different parts. So in the back of your Moore book, they give you some that you can Xerox and cut out and use. And there's some questions that involve those Quasar strips. So I would highly recommend that you either use the ones that you have from school that perhaps you have at home, or cut out the ones in the back of the book. And there are several problems that will deal with it. So they are a very good way to visualize relationships between the different strips and to understand proportionality. Okay, scale factor is a number that multiplies some quantity. Here the word scale means changing size through a multiplicative operation rather than in an additive way. Okay, and that's key. And the Quasar rods will help you with that also. Okay, a scale factor of 2 can also be viewed as a scale ratio of 2 to 1. And you can write ratios like this as well. We'll talk about ratios further on down towards the end of this book. A scale factor of 0.5 corresponds to a scale ratio of 1/2 or 1 to 2. Okay, so those are scale factors. When you talk about scale factors, it's between two objects. Aspect ratio is inside the same shape. Okay, similarity is a very specific thing in math. In terms of the geometry of it, similarity means that your sides are in proportion and your angles are identical. Okay, in everyday language, similar means showing some relationship, but in math, it's this precise relationship. So, when an object is shrunk or enlarged in such a way that all of its dimensions preserve the proportions within the original object, then we say that the objects are similar. Okay, to determine similarity, you can observe the relationships within, as I said, the internal ratios, and those are your aspect ratios, or you can determine similarity, you can observe the relationship between corresponding sides. The most difficult idea for children is to grasp about the notion of similarity is that these scale factors are involving multiplying and not adding. Remember, making that bridge to multiplication is a big one. Okay, indirect measurement. Indirect measurement is a nice thing about scale factors. So scale measurement can be used when trying to measure objects that would otherwise be difficult to measure. So if you're going to do indirect measurement like this, you can do this because the shapes are similar. So, and I'll go back over some of the geometric ideas behind this. The assumption is you have a right angle between the vertical object and the ground. So that's one angle they have in common. The second thing, because you have a shadow being cast, the angle of the sun is also constant between the two shapes. That leaves you with one more angle, and because the other two angles were the same, that has to be the same. So by definition with geometry, what I find is these two shapes are similar because of angle-angle similarity. Now that's beyond the level of our class, but knowing that, we can set up proportions, a scale factor between these two shapes. And the way you would do it is you would say that h is to 18, just like 15 is to 10. Okay, so that's doing a relationship between the two shapes. Okay, so then I can say 10 times h. Well, I think what I would do, if you want to do this, and we can do some reduction, I'm going to do that first. So I know that 3 goes into 15 5 times, 3 goes into 18 6 times, 5 goes into itself 1 time, 5 goes into 10 2 times. Then you would do your cross products. 2 times h equals 6. Okay, so hold on a second. What did I do here? Okay, let me set this up differently. I'm going to just go back. Maybe if I didn't do that. Okay, let me fix this. Okay, so we're going to do it this way. I'm going to do it between shapes. So I'm going to say that h is to 15, just like 18 is to 10. Okay, and we can solve for this problem. So what I'm going to do is divide these guys in half. So this is 9 and 5. And then I can say, when I solve, 9 times 15 equals 5 times h. And I'm going to end up with h is 27 feet. So I've solved for the height of the tree as being 27 feet tall. And I did that using indirect measurement. I didn't climb the tree and measure it. I was able to do the math of it relying upon the length of the shadow. Okay, we have one more thing, and that's talking about testing for similarity by plotting, and that's kind of an interesting thing. So that we'll do that in the next page. So testing for similarity. So here you have these rectangles. Okay, so you're talking about internal ratios here. We're using aspect ratios. So if you plot, this is the height, this is the width. If these shapes are similar, then they should all fall on the same line. And do you see how they all do except for B? Okay, so B is not quite on the same line as is the other. Let me fix that. So this is above it slightly. So the sides are not in proportion. So of these shapes, only B is not similar. Okay, so our textbook has an interesting discussion of the video industry, and that's where the aspect ratio comes up. So read that and then work through the activities, check your answer, and then we'll go over any questions that you might have.